All right, I'm back. We are on page 250. I do this in the beginning of every. I'm back. Throw my hands up. We're on page 251, and we're just going to continue. So these are going to be a little different because they're a little more algebraic. Like the last couple things that we've done have been very visual, but it's the same idea. We're going to like write some things using notation, and we're going to evaluate them as best we can. So the first thing I'm going to do is just like write it down with proper notation, right? So this will be the limit as x approaches -5. From the left is a little minus superscript of f of x, and then that's going to be equal to, all right, let's see. So I want to, well, look at this. I want to approach, oh, where are we going? I want to approach -5 from the left, but that puts me like out here somewhere where the function doesn't even exist. So this, usually in class we have a discussion about this, but this is not a reasonable question. So I'm going to erase the equals, and I'm going to say, I'm just going to say it's a bad question. Well, no, I'll say is not a reasonable question because of the domain, right? So it's not possible to approach -5 from the left. So it's not reasonable to ask what the limit is as you approach -5 from the left, because you can't do it. You can't have your little stick figure on the graph walking toward it. It doesn't happen, so it's not a good question. Value the function at x equals -5. So a lot of these feel like Algebra 1 questions. You're like, why are we doing this? Notation is super important, and one of the best ways to get it into your head is to do a lot of things that feel sort of Algebra 1-ish. So f of -5, we look, f of -5 is down there, definitely -4. You could have done that one without me for sure. The limit as x approaches -1 from the left, all right? Notation, x approaches -1 from the left of f of x is, now let's see if we can find it. Limit as we approach -1 from the left. Do I remember my color scheme? I think it was this one. So I'm going to approach -1 from the left. Like, what's the logical y value? The logical y value there is -2. So I'm going to say -2. So they're as easy as they seem. Don't get bogged down in like, oh, we're doing higher level mathematics, so it necessarily needs to be harder. Not necessarily the case. A lot of the basics are basic for a reason. So the limit as x approaches -1 from the right of f of x. All right, we go to our graph, and we change up my color again. So we slide along or walk along the graph toward -1 from the right, and you can see that you get -1. So the answer there, the expectation, the value you should have gotten in a perfect world would have been -1. You don't get that value. So here, we don't actually need the graph because we did both of these limits. Let me change my color. So the limit as x approaches -1 overall of f of x does not exist because the limit from the left is -2. The limit from the right is -1. They are both finite, but they're not equal to each other. So this is dne, does not exist. You write equals dne, whatever, live your life. So since both of them exist and are finite, the limit from the left and the limit from the right, there is a jump discontinuity. So if you look at the graph, you can see that to get from one branch to the other, you'd have to jump, which is basically where the name comes from. So there's jump discontinuity, but the limit does not exist. So the value of the function at x equals -1 is f of -1. Let's go to the graph and see what that looks like. F of -1. So when x is -1, the actual value of the function is up there. It's 1. All right. The limit as x approaches 2 from the left. So if you can knock out this page on your own, go for it. That's never a problem. Left. You know what? Maybe I'll notationally, I'll write this one too. Limit as x approaches 2 from the right. And then we'll go to the graph. So let's see. 2 from the left, 2 from the right. All right. So, like, you don't have to do all this work. 2 from the left, you can tell logical y value there is going to be y equals 2. From the right, here like this. The logical y value when you get to 2 from the right is definitely 2. So in this case, I'm going to write a 2 here equals 2. I'm going to write a 2 here equals 2. And then we know that the limit as x approaches 2 is just going to be 2 because the limit from the left equals the limit from the right equals, the limit. So the limit as x approaches 2. So no superscript there, which implies that both of them are equal. So if I only gave you I, you would automatically know the answer to G and to H. So this overall is 2. The value of the function at x equals 2, so that's f of 2, is, let's go back to the graph, f of 2 is 3 for some reason. Who knows what the reason is, but it is what it is, and there's nothing we can do about that. So 3. And let's see, the limit as x approaches -3. So this is, we're going to have to consider from the left and the right to see if those are equal. And if they're equal, we'll say that's the limit. If they're not equal, then we'll say, like, the limit doesn't exist. So f of x is, so that's why you end up writing equals dne frequently, because you like write down the notation, then you do the problem, then you're like, oh, it doesn't exist. All right, so this one's interesting because it's kind of like the first one that we've been asked about, where the function is just continuous, just working, right? So if I approach 3 here in this direction, the logical y value is -1 for sure. If I approach in this direction, the logical y value is -1. So it just makes sense to go with -1. So what color should I use? I'll use black. -1. And we get that. Okay, the next question. The slope of the curve at x equals 3. This is the first time we've tried to answer this question. So think about it. So now we're claiming that curves have slopes. And not just that, but at specific points. So this particular problem, I need to find the slope at x equals 3. The argument that we're going to make is that this is a line with a slope of whatever it is. So we go down 3 over 1, slope of -3. So doesn't it make sense that at every point on that line, the slope would be -3? Like no matter where you are, the slope to get to the next point should just be -3. Delta y over delta x, it's always going to give you a ratio of -3. I'm going to say that the slope here is -3, but this is like a big idea because we have not really discussed the concept of the slope being what am I trying to say? Oh, that a curve has a slope at a given point. So like this is linear. So we could say the slope is -3 because we went down 3 and over 1. You're going to find, though, that this is a much bigger idea. So one other way of writing that is to write, so I'm going to write dy dx. dy dx, this is going to be with you forever. So that is the instantaneous rate of change of the curve at that point. So usually in algebra, you do an average rate of change, like change in y over change in x. Here, we don't actually have a change in y or a change in x because we're at one point, but the slope exists and it's -3. Another notation for that is to say that f prime of 3 equals -3. We're going to talk about these so much that you don't really need to worry about them right now, but I wanted you to know there's notation for this. There's another notation. There's a lot of notation. We could say that y prime is equal to -3 at x equals 3. All of these are equivalent. So, and we got lucky because it was linear. So we were able to just, use what we know. But anyway, I'm going to end this video here. I will be back to do some more videos, and I will see you then.